example 3, again, is kind of similar to what we were doing in section 1. We're modeling a little bit more with exponential functions. Our slight difference here is in example 3a, we are modeling with what is called continuously compounded interest. All right, what on earth does that mean? So think about interest, okay? If you have a bank account, your bank account's constantly, you're earning interest, okay? Your bank account, you're getting rewarded for having your money in a bank, basically. As far as credit cards go, you're still earning interest, but in a negative way, because the credit card is basically loaning you money. This word compounded really means how often is the interest getting added to your account. Okay, so if you have a bank account, for example, if you're trying to save money, the more often that interest is added, the better, because then you start earning interest on the interest that's been added. If you have a credit card, the more often your interest is compounded, the worse, because then your balance is continuing to grow. Okay, what you owe is continuing to grow. We saw the equation y equals 1 plus r to the t power. Here is our equation with continuously compounded interest. Y equals p times e to the rt. What on earth does all of this mean? So p is the principal amount, your starting amount, the original. Whatever you have invested. Okay, E, you might have heard of this before. E is what we call the natural base. E is a number sort of like pi. It's an irrational number. Our natural base E is approximately 2.718, the same way that pi is about 3.14. E is about 2.718. Okay, R is the interest rate as a decimal. And then T represents the time. Now, one of the kickers for this PE to the RT formula, which we'll also call PERT, just kind of as abbreviation, time must be in years for this equation to work. Okay, so if you were talking about like 6 months, your T value in your equation would have to be 1/2. All right, so let's use this equation and an example here. Suppose you won a contest. At the start of 9th grade. That deposited $3,000 in an account. And that account pays 5% interest. Compounded continuously. You start college 4 years later. And spend 4 years in college. How much will be in the account? By the time you graduate. Okay, it's kind of a long word problem here. Before that, I'm gonna circle my equation up here. Okay, Now looking at our word problem, there's two words that we really have to keep an eye out for. And for our example, for any of our applications, if you ever see these words compounded continuously, that's your clue. We need to use this Hertz formula, y equals p times e to the RT, formula for continuously compounded interest. If you don't see these words, you will not use this formula. All right, so we see those words. Let's follow our formula. So our equation, y equals p is our principal, the original amount. We started off with $3,000 times e, which is just e, okay? It's our number, it's a base, to the RT power. R is our interest rate as a decimal. We're earning 5% interest, so that's 0.05, times our time. Well, we're in high school for 4 years, college for 4 years, so our time is 8. Okay, so this is y equals 3,000 times e to the 0.05 times 8 power. And if we plug this into our calculator, we can figure out how much is going to be in that account. So 3,000. E on your calculator is right below where pi is. Okay, if you look at my calculator here, second division puts that e value in to the 0.05 times 8 power. And make sure if you have a calculator like mine where the exponent, if you put in an exponent, it doesn't actually raise on your calculator. Make sure that you're putting parentheses around to the 0.05 times 8. So this tells us that after our 8 years, our balance would be $4,475.47. So really, once we get our equation written, there's not a whole lot of work to show because this just happens on our calculator. But that is our equation for continuously compounded interest. Again, keep an eye out for those words, compounded continuous.